Lab 4, Spring Mass Lab. The object of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. First, we will use Tracker to extract the position data of the mass. Then we will create a computational model of the mass. Finally, we will compare the model predictions with the observation data. First, we analyze the video in Tracker. We will save the XY coordinates that we obtain into a CSV file which we will use to compare our observation data with our computational model. Let's analyze the properties of our system. Our given information is that the mass is 0.402 kilograms, and that the system is at static equilibrium when the length of the spring is 0.7 meters. Using this data, we can find K, the spring constant, and L sub 0, the relaxed length of the spring. To find K, we start with the formula T, which is the period of oscillation, equals 2 pi times the square root of m over K. We can rewrite this as K equals 4 pi squared times m over T squared. We can determine T by looking at our Tracker data. The system completes 3 oscillations in 4.572 seconds. Therefore, T equals 1.524 seconds. By plugging our known values into the equation, we can determine that K is equal to 6.83 newtons per meter. To find L sub 0, we begin with the statement that the system is at static equilibrium when the length of the spring is 0.7 meters. Static equilibrium means that F net is equal to 0. If we assume that the only two forces acting on the system are the force of gravity and the force of the spring, we can say that the system is at static equilibrium when the magnitude of the force of gravity is equal to the magnitude of the force of the string. When we plug in our known values, we find that L sub 0 is equal to 0.123 meters. So, now we found K is equal to 6.83 newtons per meter and L sub 0 equals 0.123 meters. From Tracker, we also know that the initial position of the mass is negative 0.123, negative 0.6460. Now we use this data to initialize our Python program. The blue arrows indicate where we've entered all our given data and the data that we have just solved for. This section of the code sets the initial position vector and the stretch of the spring. Then we begin our while loop. The Python program solves for the forces acting on the mass. Using Newton's second law, we can translate this force data into the velocity and the new position of the mass. Then we update the position vector and the stretch of the spring for the next iteration. Now let's run the program. The blue ball is the computational model, while the red ball shows the data gathered from Tracker. As you can see, they match fairly well, especially in the y direction. There is some discrepancy in the x direction. This can be seen very clearly in the graph. The blue line shows the y position of the computational model. The red line shows the y position of the real-life mass. As you can see, they match fairly well throughout. The green line shows the x position of the computational model, while the yellow line shows the x position of the actual object. There's a discrepancy between the two, and the discrepancy increases as time passes. Some discrepancy can be accounted for by human error. For example, when marking the center of mass in Tracker. Also, if the camera was not directly perpendicular to the motion, there might have been some motion in the z direction that was not accounted for. There could also be forces acting on the system that were not accounted for in our model. For example, air resistance. Let's take a look at the energy changes in our system. Our system consists of the spring, the mass, and the earth. The change in total energy is equal to the change in kinetic energy plus the change in the gravitational potential energy plus the change in the spring potential energy. We edit the Python code to show the energy changes. Delta K is shown by the blue line. The red line shows the spring potential energy, and the green line shows gravitational potential energy. The yellow line shows the change in total energy. As the mass moves downward, its velocity is increasing, and so its kinetic energy increases. During its upward motion, the velocity is decreasing, and so the kinetic energy decreases. As the spring potential energy increases, the gravitational potential energy decreases, and vice versa. The end result is that the change in the total energy is zero. Is the energy principle satisfied? According to the energy principle, the changed total energy of the system must be equal to all of the energy transfers with the surroundings. For this system, there is no energy transfer to and from the surroundings, so delta E is equal to 0. The yellow line in our Python graph indicates that this is the case. Therefore, the energy principle is satisfied. Earlier, we solved for the period of oscillation based on y position data. If we do the same using x position data, we get a different answer. This could be because the stiffness of the spring is different in the x direction than in the y direction. Another explanation is that the oscillations in the x direction behave like a pendulum, while the oscillations in the y direction are caused by the spring force.